Streaming SIMD extensions. In computing, streaming SIMD extensions, SSE, is a single instruction, multiple data SIMD instruction set. It came out in 1999. Alright, so my question is, are they fast? And that's what this video will be about. So here's the XMM registers that came out. Most all computers have them. I'm not sure how much they're used or not. What we'll be doing is we're going to conduct a test. It will not be a SIMD test. I won't be doing multiple data, single instruction. What I'll be doing is just using the registers and comparing the speed of access to and from the registers versus the speed of accessing the stack. And in the test, I'll be using 4 32-bit integers. So each one of these XMM rows contains, it's 128 bits, so I can put 4 32-bit numbers within 128 bits. And that's the plan and the project what we're going to attempt to do today. So let's get started. Okay, in this window I have a sample program set up, XMM versus stack, and all it is a console window that gives you the press enter. So what I'm going to do is I'm going to write a function, and the first function will be a stack test. And what I want to do is I want to take a parameter called number of iterations, and the whole goal of this function will be to read and write a bunch of 32-bit values to and from the stack, and then do it in a loop, and the number of iterations will be the loop, the end of the loop. So that's how. Let's start by declaring a variable, and what I'm going to call this variable is variable 0a, and the DD is an assembly data type that means 4 bytes, which is 32 bits. The next variable I'm going to call 0b. Next variable I'll call 0c. And the next one will be called variable 0d. So I'm doing them in sets of 4 so I can kind of make it symmetrical to the XMM registers. So I have one row of variables that's 4 32-bit values, and that's going to represent the XMM 0. So let me duplicate this, and voila, there I have 5 rows of 4 variables. That's 20 variables. Okay, now let's start, and let's move into the EAX register the contents off the stack of variable 0a, which, by the way, they're all initialized to 0 value. What I'm going to do is I'm going to increment EAX to represent, to change the value. And then I'm going to move back onto the stack, the same location, the new value. So the values will be changing, and this will be our way of kind of giving us a visual aid to see that something's actually happening. So now all I got to do is duplicate this code times 20. Okay, there we have the 20 different variables being moved, incremented, and written back to the stack. Now at the bottom of my loop, I want to increment a variable that I forgot to create. Let's go up there and create the looping variable. Current. Oh, yeah, let's initialize it to 0. Okay, now we're going to compare number of iterations with current. And we're going to jump back to the top if it's greater than. Okay, that will be function number 1, reading and writing 20 different variables off the stack. And now we're ready to go for function number 2. Okay, so let's call this second function XMM test. And let's pass in number of iterations. Make it the same. Okay. Again, I need to have a looping variable initialized to 0. And I'm not going to need any locals because I'll be using the XMM registers. But I would like to zero them out. And the PEXTRD is a great way to zero out a register. So I guess I kind of lied earlier. I said I wouldn't be doing any SIMD instructions. I think the PEXTRD is actually a SIMD instruction, so I guess I'm using one. There's XMM2. So how many are we going to need? Let's see, 20 times 4 is 5. So we got a couple more to go here. 3, 4. Alright, so that should be 20 variables. Alright, let's go ahead and I didn't do this down here, but I think I should probably do it. Just in case there's junk in the upper portion of the register, I don't want to have to look at it. Okay. No ops not necessary. I like to throw them in every once in a while to help me find where I'm at. Okay, so what I'm going to use now is an instruction called PEXTRD. It's an extraction instruction for moving data. And the D at the end tells the size, which is be 4 bytes or 32 bits. So the first parameter, by the way, first parameter is register memory 32, then an XMM register, and then an immediate. Okay, I'm going to start out with EAX as the destination, and my source will be XMM 0, and this immediate, if I type a 0 there, that will access the far right side of XMM 0, which is the lowest order bit. Then I'm going to do the same thing. I'm going to increment EAX, and now it's to put the value from EAX back into XMO, and to do that I'm going to use a command called PINSRD. Again, D meaning 4 bytes or 32 bits. And this time the destination will be XMM 0, source will be EAX, and the immediate will be the same. Okay, so that's how to read, increment, and write. So now all I got to do is duplicate that 20 times. Before I do the duplicate step, I'm going to type one more in on the video here. So for the next one, it's going to look the same. The same destination register, the same source register, but this time if I change the immediate to a 1, then I'm going to be accessing the next 32-bit number in the register. So that's how you do that. And then I insert destination XMM 0, source EAX 1 again. Okay, let's duplicate that. Okay, there I have 1620 read, increment, and write back and forth in and out of the XMM registers. Now I want to increment our looping variable and compare the number of iterations with our looping variable and jump greater than to make the loop run. So if you kind of look at that, you can see that between this no-op is all my XMM4 registers, and it has a pattern of 3210 for the immediate. Here's the XMM3 registers with the 3210, and the 2s and the 1s and the 0s, and so there's 20 reads, increment, and writes, very similar to the stack test. Okay, so now we have two tests. What I'm going to do now is I'm going to make a function. I'm going to call it perform a test. And in this one I'm going to invoke the XMM test, and I'll give it a test number of, let's say, 5, and invoke the stack test, give it a test run of 5, and then up here in our main entry point we're going to invoke perform a test. So that function will call here, which will call that test, and then that test, and that right there is a good point to, before we continue typing, to try to compile and run this program and see what this looks like and see if we got this working. Let's go for a create exe. That's a good sign. And I could do run right here, but then I wouldn't be able to see anything. I've got nothing printing to the output. So in order to see what's going on, we have to go to the debugger. Okay, here we are in the debugger. This is on the main entry point. I'm going to go into this perform a test, is this function. We're going to go into that one. And within that one, it's going to perform the first test, which I believe is the XMM test. It happens to be right here. So R10 is what's been assigned as our current, which will be our looping variable. You can see on the right the XMM registers are displayed. So this PXOR will zero out the registers that are already full of zeros. And that'll zero out the RAX register, which is off the screen. And there's our first no-op. Okay, so we extract a 0. You won't be able to see a 0 being extracted, so I'm going to kind of skip over that. Increment a 0. We can see that. Let's go up and check that out. There's that red line there on RAX. You can see that it's now a 1. And now we're going to insert that back in. And you can see XMM 0 has a 1 at the lowest location. So likewise, we're going to extract a 0, increment to 1, write a 1. Now you see that the 1 was written about 4 bytes away from the first one. That's how that works. I'm going to go a little faster here. You can see the whole first row just got done. There's the 4 values. Now we got our first no-op. Alright, now we're going to do in the XMM1 registers. And that's going to do the same thing. I'm going to go kind of faster here. And there's, you see that the first whole iteration of the loop is all about incrementing from 0 to 1 and reading and writing all 20 of these values. And I went a little too quick there. We just jumped back to the top of the loop. Sorry. Alright, now we're going to do XMM 0. And we just incremented EAX. Let's go up there. See, RAX is 2. And now we're going to do the insert command to put the 2 in. So, as you can tell here, hit go a lot faster here. Every iteration of the loop, you can see it counting in the registers. So what we're doing is we're reading, incrementing, and writing to and from the XMM registers, just like we want to do perform the test. Alright, so I'm going to make this go execute to the end. And I'm on the return now. You can see that a 5 is in the position, so it ran the loop 5 times just like we want it. And that's that test. So now the other test will be the stack test. Let's go into that one. So now the stack test has a little bit of extra overhead up top of the initialization, moving zeros in and making sure the stack is zeroed out. There's the XOR of RAX, not necessary, but there it is. So here's the first move. We move a 0 into RAX, and I can move this window up so we can see that, because we don't need to look at the XMMs any longer. You can see the RAX got incremented to 1, and now when I move that back to the stack, that line executed, you can see the 1 is down there on the line that was turned gray there on the right bottom right corner. Let's do another one. I'll kind of go fast here. So as you see the 1's populating on the stack, you can tell where they're sitting, and that it is working. It is actually, again, reading and writing to and from the stack. And here's the bottom of our loop. We're going to do this 5 times. So now you see it. If I hold this button down, you can see it going a little faster. Reading and writing to the stack and incrementing. So the test is working. We're almost ready for a time test. Let's run this full speed, and there's our DOS window somewhere. Let's see if I can find it. There's our DOS window. Didn't show anything, nothing got printed. There's press enter. Program over. Alright. Okay. We're back here at the compiler. So our tests work. We know that it works with 5. Let's make now we got to set it up to be a time test with a lot of iterations. So let's make a local variable. Call it number of iterations, and let's set it to be something kind of big. How about that? That's kind of big. Also, we're going to need a local variable for keeping track of time. So I like to use the DQs, again, an assembly data type. All it means is 8 bytes. And we need now to invoke a timing function, and I'm going to be accessing the Win64 API for that. And I believe it's called get tick count. There it is. Get tick count 64. I've used this before. I like using this function. It returns its result in RAX, 8 bytes, and I'm going to store that in start time. And what that really is, it's not really a time. It's actually the count in milliseconds since your last reboot, I believe is what it is. So it's a millisecond counter. And then it's going to invoke a function, or the test function. Okay, and down here, after the test, I need to invoke the function again. Oop. And then I need to take that result, it's now an RAX, and subtract from that the start time, and that'll give me the time it took for the function to run. Now would be a good time to report something to the screen. So I'm going to use, this is kind of new if anyone's watched my other videos. I used to be prints.print. I've been working on rewrites to get all my character encoding to be the UTF-16. And I've changed things around a little bit, so now I do console.write and console.writeLine. So lost my IntelliSense there. Okay, so I've got 3 different functions here that are WriteLine. I'm going to use XMM test. That'll be a string. And then I get to give it a number, and I'm just going to throw it RAX. And this third parameter is a little new and doesn't really work yet, and it's the IntelliSense isn't really right because it says enum. Well, okay, yes, it is an enum, but I don't want you to say enum. Anyway, I know what it is, and I'm working on the syntax, so let's just get through this. Console dot enums dot number format dot decimal and hex. Okay, so I'll tell you right now, decimal will give you hex. So I might as well ask for hex because that's what I'm going to get anyway. Okay, and there is our WriteLine. That's the first test. And now we have to just kind of do the same thing for the next test. I'm going to do some code copying here. And we just got to change this to stack test. Stack test. And I believe so these 2 guys are kind of unnecessary. How's that look? Alright, I think we're finally ready to run this test. Let's give it a compile real quick, see what we get. Okay, I don't know what I'm doing sometimes. I just start deleting things and everything gets out of control. Iterations. I need that in there, and I can't delete this line because this line here, that's kind of an important line to have in there. Say number of iterations. There, I got some color. What's wrong with this guy? Number of okay, finally. I think we can compile. Let's give this a shot here. Well, that's a good sign. How about a run? Ooh, something's happening. It's taking a little bit of time. There's an XMM test, and there are some results. And that is not what I had expected, to tell you the truth. It shows here that the XMM test took longer than the stack test. Every fiber in my being was telling me that registers are faster than memory. And I still believe that, but not during this test. So I guess first is how much slower are the registers? That would be my first question. And let's type in 1A 35 4 divided by 878. 3. Okay, so this isn't floating point math, so I'm just going to say about 3 times slower is what the XMM registers were, which is kind of a big deal. So what this tells me is that accessing data using the extract and insert is slower than accessing the data that's on the stack, which I would not have guessed. But I do know that when you do SIMD processing, and I have a few other videos out there that prove this, that when you do things in SIMD and you actually use the SIMD instructions, and when you do an addition, there's actually 4 additions happening and things like that, that it is 10 times faster than the old way of just using regular registers. But in this test, it shows that if you're going to use the XMM registers for data access and not really use it for SIMD, then it's slower than the stack. So I guess you just got to be careful. You got to know what's quick and what's not quick. Because what's happening here is each one of these instructions that Intel's building, or these CPU manufacturers are building, each instruction can have a lot of code that you're not seeing, a lot of executions, a lot of CPU cycles, and you don't know which ones are quick and which ones aren't. I mean, you kind of do know. I mean, you've heard things like we all know that multiply and divide are take a lot of CPU cycles, but addition is quick. But other than kind of just knowing because you've heard, there's no real speed gauge anywhere or any indicator that helps you know. And when you do things, I guess you just got to test and kind of learn and figure it out. So hopefully this helps people. If you're thinking, like, have an imagination or a dream like I had about using these XMM registers for data, storing stack variables and such, this little experiment should prove to you that just storing it on the good old-fashioned stack is quicker, and as we all know, it works quite well. Likewise, since 1999, these XMM registers have been extended from 128-bit to 256-bit, and now they're up to 512-bit. The XMMs are still 128-bit, but the extension's called YMMs, and to the 256, and the extensions to 512 is called ZMMs. And the XMM and the YMM overlaps within the ZMM. If that makes any sense, I don't know. It's kind of like, I think you know what I'm talking about here. It's kind of like EAX is within RAX. They're overlapping. Anyway, thanks for watching. Hope you enjoyed. If you like this video and videos like this, please give me a like and subscribe. Helps me to continue the motivation to keep doing silly stuff like this. And thank you for watching.